Hi everyone, this is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in this session, I want to discuss about stress strain diagram. This diagram is very important for mechanical engineering components design. So I will explain. So what are the properties involved in this stress strain diagram? So this is called as stress strain diagram. So stress versus strain diagram drawn, and x-axis strain, and then y-axis stress values are noted here. So it is drawn between the stress and strain. This diagram drawn from the obtained results from tensile test. A standard specimen taken for design testing purpose. So here shown the specimen. This specimen, the shape of the specimen after elongation here shown. So here, before elongation it is a circular one, and the just like a shaft. So before going to explain this stress strain diagram, so I want to discuss about the mechanical properties. So what are the important mechanical properties? So already you know the mechanical properties are strength, hardness, ductility, malleability, elasticity property, and plasticity property, creep, and etc. properties are there. But before designing or any component of mechanical component or mechanical mission. So suppose you take one mission, a mechanical mission, having number of components. So each and every component you should design before assembling. So, but before designing, you should know about its nature. So about its nature means in terms of the properties, material properties, in terms of environmental conditions. So actually the components, how they will function in a actual condition. So without knowing the mechanical properties, suppose you have designed a component and release it into market. So what will happen? So who will purchase your component? So you are not tested, you are not taken any opinion from the customers, you are not implemented as per the design standards. So ultimately your design will fail. So that every design engineer should know about mechanical properties. For a material selection, if you have selected a good material, it gives good results. If you are selected wrong material for a good design, so what will happen? The design will fail due to the wrong selection of the material. So that before selection, so you should know about the properties and composition of a particular material. So that you need to use this stress strain diagram. So by using this diagram, you can calculate the properties, all from mechanical properties, and you can calculate stress values for particular load. So by using a load and cross-sectional area, so that in engineering, in mechanical engineering, so one machine is there, that is universal testing machine. So by using this machine, you may calculate, you may determine the mechanical properties of a material. Take example, mild steel. So mild steel properties you may determine by using this testing of specimen. Okay, so this by using this tensile test machine, you may calculate stresses at a different levels of loading. So you may gradually increase the loads and observe the component. So what will happen? So how they elongate corresponding to the applied loads. So at particular point, you may calculate, you may determine stress strength values. So all these values you may plot on this the stress strain diagram. So that's why very important this the stress strain diagram for a mechanical engineer. So here shown one line, straight line from 0 to A. This is a straight line. So this straight line up to this 0 to A is called as elastic limit. I will explain. The professional limit means it's also called as the elastic limit level. We see from the diagram, from the point O to A is a straight line. So which it represents that the stress is proportional to strain up to A. So there is no difference. Suppose here stress value equal and strain similarly. So like this, the stress is directly proportional to strain. Suppose the stress value increased, the strain also automatically, the strain value also will increase. Suppose strength value decrease, the strain value also will decrease. So proportionate. So the curve slightly deviates from the straight line behind this point A. See here the curve is after this slightly deviate. Zero to A and slightly deviate. So it is it maintains Hooke's law and holds good up to point A, and it is known as a proportional limit. It is defined as that stress at which the stress strain curve begins to deviate from the straight line. So at this level is called as elastic limit. So up to A, O to A, the material is within the elastic limit. So yeah, as per Hooke's law. So what do you mean by Hooke's law? Hooke's law means stress directly proportional to strain. So stress you may represent with sigma proportional to strain, epsilon. So you may write sigma is equal to E multiply with strain. This is Hooke's law. So here E is here Young's modulus. So Young's modulus, it is a constant. So E is equal to sigma by stress per strain. This is a relation between stress and strain. It gives Hooke's law. The second point is elastic limit. So it may be noted that even if the load is increased behind point A up to the point B, the material will regain its shape and size when the load is removed. So that's why this point is called as elastic limit. This means the material has elastic properties up to the point B. Thus here, even though slightly deviates from A to B behind A, but it maintains elastic limit. So elasticity property means the material regains its original shape after removal of load. So here also happens same that the material has elastic properties up to the B. Suppose whenever you remove load, it regain its original shape. So this point is known as elastic limit. It is defined as the stress developed in the material without any permanent set. So there is no permanent deformation. So whatever obtained, the deformation is temporary deformation. So why? Because due to the elasticity property. Next, third one, yield point. After B point, if the material is stressed beyond point B, the plastic stage will reach, that is on the removal of the load. The material will not be able to recover its original size and shape. This property is known as plasticity. Is the reverse of elasticity property. So whenever you remove the load, the material will not gain its original shape. So that the strain increases at a faster rate with any increase in the stress until the point C is reached. After this point, the B point, at C, what will happen if the small value of strain increases, the stress increases, the strain automatically increases. So at this point, the material yields before the load and there is an appreciable strain without any increase in stress. So at this point, we not increasing the stress, so the appreciable strain also will occur. Due to the yield position, so this state is called as a yield stress state, plasticity zone. In case of mild steel, take a mild steel example. Mild steel is a ductile material. So it will be seen that a small load drops to D here. So again from C to here A and B, C and D. So it drops down. Immediately after yielding commence. So here means there are two yield points, one is C and another one is D. The points C and D are called the upper and lower yield points respectively. So here this one is upper point and D is the lower point. The stress corresponding to yield point is known as yield point stress. See, so in this example taken here, mild steel. So C is already yield point started after point B. So the material will not regain its original shape after removal of load. So here two types, again a small load drops down to D. So C and D are called upper and lower yield points. So these corresponding stresses are called as yield stresses. Yield stresses at C and yield stresses at D. Actually, here these two values are almost same, the upper and lower. There is no larger variation. So sometimes that's why in while problem solving may be taken as same. Fourth one is ultimate stress. So at D, the specimen regains some strength and higher values of stresses are required for higher strains. Then those between A and D. So ultimate stress, this is the maximum load that component withstand, the specimen withstand the stress. So suppose you are increasing the load, you are gradually increasing, so goes on increasing, then what will happen? Till the point E is reached. So already here entered into yield state, yield plasticity zone. You are increasing the load, so yielding, so up to E, so it reaches the maximum point E. Ultimate stress, maximum stress. Beyond this stress, the specimen will not tolerate. So it means it can withstand this up to this E point stress only, the corresponding value, stress value at E. So what is the stress value at A, B and C? You may calculate. So the gradual increase in the strain or length of the specimen is followed with the uniform reduction of its cross-sectional area. So cross-sectional area also may be decreased. Why? Because the length varies. So change in length, the strain means the change in length upon by original length. So how much length decrease or increase. So that here the work done during stretching of the specimen is transformed largely into heat and specimen becomes hot. At E point, so you are increasing load, so it reaches the maximum limit E. Beyond this E, what will happen? Attach the maximum value. Beyond this E, the component will gain some heat. It becomes fail after behind the point E. So that this stage is called as highest, the ultimate stress zone. So next, fifth one is behind the ultimate stress, breaking point. So after the specimen has reached the ultimate stress, so neck formation is formed. The specimen is like this. So neck formation. So neck formation will be occurred. So that the stress necessary to break away the specimen is less than the maximum stress. This point is called as breaking point, and then at this point available stress is called as breaking stress. So what is the breaking stress for this specimen? You may calculate. Now you may determine the percentage reduction in area. So it is difference between the original cross-sectional area and the cross-sectional area at the neck before fracture and after fracture. This difference is expressed in terms of percentage. So that is let A original cross-sectional area and the small A is a cross-sectional area at the neck. So the reduction in area is original area minus neck area. So the percentage reduction, so you may calculate. So how much decrease reduction in area A minus A by original length divided by A multiply with 100. Next, percentage elongation. So it is the percentage increase in the standard gauge length. So that is standard gauge length means original length obtained by measuring the fractured specimen. So after bringing the broken parts together. So what is the original length and after what is the change in length? So the original length is called as gauge length. The capital L is length of specimen after fracture or final length. So elongation is take the difference between these two, the original length minus length of specimen, you will get elongation. Now percentage elongation, L minus L by L multiply with 100. Yes, small l is the original length. Capital L is length of specimen after fracture. Clear? So these 7 points are very important in problem solving point of view for designing any mechanical component with the help of stress strain diagram. Next we will see one problem. A cast iron link as shown in figure. This is a cast iron link is required to transmit a steady tensile load of 45 kilonewtons. Find the tensile stress induced in the link material at sections AA and BB. So here given specimen, here tensile load 45 kilonewtons and the link, cast iron link shown in this figure. Inside you have dimensions in section, sectional view, section at BB. Have to calculate tensile stress induced in the material, in the link material at sections AA and BB. So what is the tensile stress at this section, and similarly what is the tensile stress at BB section, have to find out. See, given values are P is 45 kilonewtons, convert into newtons, 45 into 10 cube. Tensile stress induced at section AA means we know that cross-sectional area of link at section AA. So area find out. Area is 45 into 20. So at this section, length into width 45 into 20, 900 mm square. Tensile stress induced at section AA, you may calculate by using this stress relation. Stress is equal to load for area. So here load is 45 kilonewtons. Area is 5 by 4 into, sorry, here this is not a circular. So rectangular, 45 into 20 area, length into breadth. So another area you have to find out at a section BB. So that is tensile stress induced at section BB. So here find out the cross-sectional area of link at section BB is 20 multiplied with 75 minus 40. So here plate having a hole. So 75 minus 40 here, 75 minus 40, 35, multiply with 20. So you will get 700 mm square area. Now calculate tensile stress induced at section BB. Sigma BB is equal to sigma tensile stress sigma T at BB section, load for area. Load per area. So here load is 45 kilonewtons upon by area. So 64.3 Newton per mm square. So we will get 64.3 megapascal. So one more problem we will see. A hydraulic press exerts a total load of 3.5 meganewton. So this given component hydraulic press, this load is carried by two steel rods supporting the upper head of the press. The safe stress is 85 megapascal. E is equal to 210 kilonewton per mm square. Here he has asked to find the diameter of rods, extension in each rod in a length of 2.5 meter. So P is 3.5 meganewton and sigma T is 85 megapascal and E is 210 kilonewton per mm square. So substitute here convert 210 kilonewton per mm square into Newton per mm square, 210 10 cube Newton per mm square. So similarly L also convert, L is equal to 2.5 meters, convert into mm. So and then find the diameter of rods. So let take D, small d is the diameter of rods in mm. Find out the area, 5 by 4 into d square. Substitute d value. So here in terms of d, you will get 0.87854 d square. You have to find the diameter of the rods. Here load P is carried by two rods. Therefore, the load carried by each rod is divided by 2. In your problem, the load carried by two steel rods. So that the given load is 3.5 meganewton, convert into newtons. So 3.5 into 10 to the power 6.2. The load carried by each rod is P1, 1.75 10 to the power 6 is equal to sigma T into A. So as per stress, load for area. So the load is sigma T multiply with A. So sigma T given in a problem 85 megapascal safe stress, convert into Newton per mm square. So that is 1 megapascal is equal to 1 Newton for mm square. So that substitute here and here you may determine diameter of the rod. 162 mm you go. Similarly, next second step is extension in each rod. How much elongated? So the extension in each rod is delta L. So delta L, so here take Young's modulus formula. Young's modulus is equal to E is equal to PL by A delta L. So it means delta L is equal to PL by AE. elongation. So from this relation, you may write E is equal to PL by A delta L. So this is P1 into L by A into delta L. So that sigma T into L by delta L. So substitute all those values. So you will get delta L 1.012 mm. This is the extension in a rod, each rod. Like this, I have to calculate. So these are the references I have taken. B. Bandari and R.S. Kurmi and R.L. Norton. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.